CQC, Chapter 4, Resolution of Primordial Cosmological Anomalies. Here we will address one of the hottest and most current problems in modern astrophysics. Why is the James Webb Space Telescope observing massive and old galaxies dating back to a mere 300 million years after the alleged Big Bang? For standard physics, this is an insoluble paradox. For us, it is a beautiful problem of geometric compression and elasticity of space. 4.1. The paradox of mature galaxies in the early universe and the concept of compressed space. Observations conducted by the James Webb Space Telescope have revealed the existence of massive, structured, and chemically mature galaxies at high redshift values, corresponding to just 300 to 400 million years after the estimated Big Bang. In the standard cosmological model, the formation of such structures in such a short time frame is statistically and physically almost impossible, as gravitational aggregation processes require significantly longer timescales. CQC elegantly resolves this cosmological anomaly by demonstrating that the early universe was not young in terms of chemical-physical evolution, but was instead characterized by a compressed spatial geometry that distorted our measurement of cosmic time. Imagine a closed accordion. If we trace 2 points on the surface of the bellows when it is fully compressed, the actual geometric distance between them is tiny. But if we stretch the accordion, the distance between those same points becomes 50 centimeters. At the beginning of the eon, right after the primordial collision between the brains, the lattice of space strings was in a state of maximum compression. What does this mean in mathematical terms? It means that the density of space building blocks per unit of macroscopic volume was extraordinarily high. We define this linear density of space strings as ρs. In the early universe, ρs. If today a photon needs to traverse billions of space strings to travel from one galaxy to another, in the early universe the actual distance measured in string hops was infinitely shorter. Space was literally compressed, just like our accordion. 4.2 spatial compression, the photon's optical path, and the illusion of primordial time. At the beginning of each eon, immediately following the inelastic impact between the brains, the lattice of space strings is in a state of extreme two-dimensional compression along the surface of the brain. This means that the linear density of space strings per unit of macroscopic distance is incredibly high. ρs. Let us imagine that to cover a macroscopic distance that today requires n building blocks, in the early universe only a tiny fraction was needed, for example n1000, because the lattice had not yet stretched. When a primordial galaxy emitted a high redshift photon, that photon had to travel across an extremely reduced number of physical strings to reach the region of the brain we occupy today. Consequently, the actual time taken by the photon to traverse the compressed primordial space was far less than what is calculated assuming static or uniformly expanding space. The actual distance traveled was geometrically reduced, although our subsequent expansion stretched the geometric floor of the lattice, moving the space strings apart and lengthening the wavelength of the traveling photon. Lambda observed equal to lambda emitted ρs. Here we apply a classical concept used in geometrical optics, the optical path length. When light passes through a dense medium, it slows down, and its apparent path changes. In the early universe, light emitted by a galaxy had to traverse a lattice of strings that was extremely dense, yet geometrically very short. From the photon's perspective, the trip was lightning fast because there were very few building blocks of actual distance to overcome on the brain. However, while that photon was traveling toward us, the fabric of the universe stretched out. The space strings moved apart from one another due to the relaxation of the residual strain tensor SMU that we saw in Chapter 1. When we measure the light from that primordial galaxy today, we see it strongly redshifted. Standard astrophysicists look at this redshift and calculate travel time, assuming that space has always been uniform and extended, arriving at the erroneous conclusion: this galaxy formed in just 300 million years from the Big Bang. Instead, the mathematics of CQC tells us that the redshift z is a geometric stretching redshift linked to the density ratio of strings between the moment of emission and reception. 1 + = tau s rho s. The explanation of the paradox. JWST galaxies did not form in 300 million years. They had billions of years of actual evolutionary time available to rotate, condense, and fuse heavy chemical elements within their stars. The early universe was simply much more compressed and compact than we think. Light traveled a reduced, real distance, and only subsequently did the dilatation of the spatial fabric stretch the wavelength of the traveling photon, granting us the optical illusion of a newborn universe. 4.3 Resolution of the age of the cosmos and the equation of state of compressed vacuum. This redshift is not caused by hyper-fast primordial recessive kinematic recession, but by the subsequent elastic stretching of the space fabric strings during the relaxation of the residual strain tensor SMU. As a result, the galaxies observed by JWST at Z15 did not form in a mere 300 million years from the Big Bang. They had billions of years of real evolutionary time available to aggregate, rotate, and enrich themselves with heavy metals in a universe where the geometric space between them was simply incredibly denser and more compressed. The illusion of an extremely young universe is an optical geometric effect due to the original density of the space string lattice, which drastically reduced the initial transit time of light. To lend rigor to this concept, we can write a simple equation of state for the fabric of space understood as an elastic quantum fluid. In classical thermodynamics, the pressure P and volume 5 of an ideal gas are linked by Boyle's law. In our modern ether, the elastic pressure of space strings and their linear density are linked by a quadratic equation of state, due to the head-to-tail contact interactions of the strings on the brain. PS = tau s2, where W is an elastic coupling factor that depends on the impact energy of the ion. The quadratic term ρ s2 indicates that the more compressed space is, the closer the strings are, and the greater the elastic pressure pushing space to expand. This extremely high primordial pressure is what provided the impetus for the initial expansion, a purely mechanical process of decompression of an elastic medium, without any need for initial dark energy or mathematical singularities.